Welcome to AI Paperslop, the YouTube series where we summarize the latest AI and tech papers for researchers and ML engineers. Today we are jumping straight into a paper out of the University of British Columbia by Kevin Murphy, and it's called Model Discovery Agent, LLM-assisted diction experiment designed for data-efficient discovery of mechanistic world models.
Quite a title, yeah.
Yeah, right. But here is the 60-second core summary of what you actually need to know. This paper introduces the Model Discovery Agent, or MDA. If you've been, frustrated by LLMs just acting as these sophisticated curve fitters on passive data, MDA is basically the antidote to that.
Right, because it couples large language models with actual rigorous Bayesian machinery to discover latent causal mechanism.
Exactly. So the LLM acts as the initial hypothesis proposer. And then sequential Monte Carlo estimates the parameters and structure, while value of information drives the actual Bayesian experiment designed to collect new data. It's setting new state-of-the-art records across physics, chemistry, and even this brand new biology benchmark.
And it does all this by effectively operating in the MOpen setting, which is...
Right, where the true mechanism isn't even in the initial hypothesis pool at all. We're talking about, actual causal scientific discovery here, not just next token prediction.
Yeah, it fundamentally shifts how we should be thinking about AI for science. I mean, for a long time, the community has just been stuck hoping that if we just scale the model up, if we just feed it enough passive observational data, it will magically infer the underlying physical laws of the universe.
It'll just grot quantum mechanics if we give it enough tech.
Exactly, yeah. But this paper proves mathematically why that approach just hits a wall, and it gives us the formal tools to let the agent actively interrogate the system instead, which is huge.
Right, so let's unpack this whole trap of passive observation. The paper is hyper-focused on building mechanistic models. As ML engineers, you know that if you want to answer interventional, what-if questions, what happens if we administer this completely novel drug or launch a probe on some wildly untested orbit? You need a causal model of the data-generating process.
Yeah, this is level 2 on Judea Pearl's ladder of causation. You're intervening.
Exactly, level 2. And that causality is entirely inaccessible if you only have passive data, because passive data fundamentally underdetermines the model.
Right. Think about the concept of degeneracy in physics. You can easily have two entirely different causal mechanisms that produce the exact same historical data.
Oh, totally.
So they'll overlap perfectly in your training set. But the moment you introduce a new intervention, like something that pushes the system out of distribution, those two mechanisms are going to yield wildly different predictions. Passive observation just leaves those mechanisms completely unidentified.
Yeah, the analogy I like to use is, imagine you're watching a car drive, but you're sitting in the passenger seat. You can fit a beautiful curve to its path, right? You can predict where it's going to go next based on its momentum.
Yeah.
But because you're just watching...
I don't know what's driving it.
Right. You have absolutely no idea if the steering wheel or the pedals are making it turn. To figure out the cause, you have to actively intervene. You have to literally reach over and grab the wheel. But if you look at standard reinforcement learning, it just tries random interventions. It just yanks the wheel and slams the pedals just to see what happens.
Which works in a simulation, but...
But this paper argues that random interventions are way too expensive for real science. We need rigorous Bayesian experimental design to pick the exact right pedal to push.
Because cost is the absolute bottleneck here. If you are an AI scientist running a real-world lab assay or a, phase 2 clinical trial, every single experiment costs massive amounts of time and money.
Yeah, you can't just run a million trials.
Exactly. So your core metric cannot just be predictive accuracy on some holdout set. Your core metric has to be data efficiency. You need these deliberate, mathematically optimal interventions to break that degeneracy between competing hypotheses using the absolute minimum number of experiments.
Okay, so how does MDA actually, calculate which experiment to run next?
Let's look under the hood at the architecture. It's this pretty wild fusion of old-school Bayesian stats and modern LLMs. The system starts by feeding a natural language description of the domain into an LLM.
Right, just asking it to brainstorm candidate mechanisms?
Yeah, exactly. And then what?
Well, this is where we hand the keys over to the Bayesian machinery. Once the LM spits out a batch of structural hypotheses, the system uses sequential Monte Carlo, or SMC, to compute the posterior over both the parameters and the structures of those models.
Okay.
And what's really fascinating here is how the math itself enforces discipline. The Bayesian integration over the model parameters naturally acts as an automatic Occam's razor.
Wait, Occam's razor, because it's penalizing the LLM for proposing overly complex models. Yeah, but it goes deeper than just the simple, penalty term that you'd tack onto a loss function. In Bayesian evidence calculation, the marginal likelihood, you are integrating over all the free parameters.
Right.
So if an LLM proposes a massive, highly complex equation with, say, a dozen free parameters, the probability mass is spread incredibly thin across that vast parameter space. Unless that specific complexity provides a massive proportional spike in how well it fits the observed data, its overall integral is just going to be lower than a simpler model.
Oh, wow. So the math organically starves the overly complex, inelegant structures.
Exactly.
I love that. It's essentially a classic good cop, bad cop routine. The LLM is the creative brainstormer throwing out wild structural hypotheses based on its vast training data. And the Bayesian math is the ruthless accountant.
That is a perfect way to put it.
Right. It just proves which idea actually holds up to the math and ruthlessly penalizes the LLM if it uses too many parameters.
Yeah, and that tension is what makes the architecture work so well. The LLM provides the broad creative priors, and the Bayesian side provides the epistemic rigor. And once we have those evaluated hypotheses, MDA handles the experiment design by maximizing the value of information, or VOI.
Value of information.
Yeah, VOI doesn't just look for where the model is uncertain. It specifically calculates which potential experiment will cause the current competing hypotheses to disagree the most. It ensures maximum information gain.
Okay, but, and here's where I want to push back a bit, all of this architecture assumes the LLM actually guesses the right structure in that very first brainstorming session. What happens if the true physical law is just simply not in the LLM's initial brainstorm? Like it's just completely absent.
Yeah, so in Bayesian terms, you've just described the M-open regime, meaning the truth lies outside your initial hypothesis class. And this is traditionally a fatal flaw for pure Bayesian updating.
Because it can't evaluate what isn't there.
Exactly. A Bayesian update can only shift probability weights among the existing hypotheses. It literally cannot invent a new one out of thin air.
So how does MDA handle it?
This is where it gets really clever. MDA handles this M-open problem with a predictive check. It looks at the current maximum A posteriori model, an MAP model, which is the current front runner, and runs an out-of-sample predictive forecast.
Okay, so it checks its work.
Right. And if that model fails, meaning its residual error crosses some predefined threshold, it triggers an alarm. MDA wakes the LLM back up, forces it to look the unexplained residuals, and says, generate a brand new batch of hypotheses to expand the pool.
Oh, I see. It dynamically grows the hypothesis space, but only when the data proves the current space isn't sufficient.
Exactly. But if you're an ML engineer listening to this, you're probably immediately wondering about compute bloat.
Oh, yeah, absolutely. If the LLM just keeps dumping new equations into the pool every time it's confused, your sequential Monte Carlo is going to choke.
Right, which is why MDA prevents this by using an ESS adaptive pool. ESS stands for effective sample size. If the system finds a model that fits beautifully, the posterior becomes highly confident, and the effective sample size drops because all the weight is concentrated on just one or two models.
Okay.
When MDA sees this, it aggressively prunes the near duplicates and the failed hypotheses, shrinking the number of hypotheses to let the posterior concentrate.
Wait, hold on. Let me just ask about that LLM generation step.
Yeah.
If the LLM is just rapidly generating new formulas because the residual error got too high, aren't you running the risk of it just cobbling together a Frankenstein equation?
Raymond?
Like it just memorizes the noise in the data without actually grokking the underlying physics? It just stitches together math until the error drops.
Right. That is the defining vulnerability of traditional symbolic regression. But remember our ruthless accountant, the Bayesian Occam penalty? The SMC integration fights off those over-parameterized Frankenstein equations.
Right, because the probability mass gets spread too thin.
Exactly. And we actually get to see this play out perfectly in the physics benchmark they ran, which is called ForceBench. We can literally map the exact moment the AI discovers a new physical law.
Yes. Let's dive into ForceBench, because this is where the rubber meets the road. The task here is for the agent to discover two-dimensional force laws, like gravity or, fractional Laplacians. And the breakthrough example in the paper is what they call the Yukawa world.
Yeah, the Yukawa world. In this environment, the true underlying force is governed by a modified Messel function. It's K1 of R over lambda, all divided by lambda.
Right, and the trick here is that at short ranges, this complex Bessel function looks mathematically identical to a simple inverse power law, like 1 over r squared.
Exactly. And if we connect this back to our earlier point about passive data degeneracy, this is the ultimate trap. If you only have observational data gathered at short distances, the true Yukawa potential and the simple inverse square law are perfectly degenerate. They completely overlap.
So if you use a random experimental design, the agent will probably just keep dropping probes at short ranges, and the models remain tied forever.
Right.
It's basically like trying to figure out if someone is a marathoner or a sprinter by watching them walk around a grocery store.
I love that.
They look identical, right? You could watch them buy cereal for 10 years and never know which one they are.
But MDA's value of information algorithm realizes this ambiguity. It calculates that the predictive variance between the two formulas only diverges at long distances. So it explicitly chooses a long-range probe. It drops a probe at a radius of 6, which is well past the screening length of the Bessel function.
So it deliberately designs an experiment that forces them to run 5 miles to break the tie.
Exactly. That single, perfectly placed probe forces the hypotheses to split. If you look at the accuracy complexity of Pareto frontier in the paper, you literally see the true model suddenly drop into the convex corner.
And what's wild to me is that because the voice is so efficient, MDA allows a relatively cheap base model like the used DeepSeek V4 Pro 2 to achieve near Opus 4.7 accuracy in just a handful of experiments. It massively outperforms pure LLM agents.
Because pure LLMs just keep watching the runner in the grocery store. They just ask for more and more observational data that contains zero new causal information.
Right. Okay, so physics is great. The math is clean, elegant. But let's shift gears to empirical chemistry, because we both know nature is messy. This brings us to ChemBench. Here, the agent has to map 7 continuous inputs, things like substrate inhibitor pH, temperature to a reaction rate.
Yeah, chemistry introduces massive multivariable complexity. And to benchmark MDA here, the authors compared it against the previous state-of-the-art system called LLM-auto-Scilab, which relies heavily on PSR, a popular symbolic regression tool.
And they exposed a huge flaw in that PSR approach. The paper calls it a high-exact, low-symbolic pathology.
Yeah, that's a great term for it.
Right. If you look at LLM-auto-Scilab's results, it achieves this astonishing numerical accuracy. We are talking about a root mean square log error of 0.001. But if you actually look at the formulas it spits out to get that score, it's just unphysical nonsense.
Yeah, it's nesting logarithms inside stretched exponentials. It's overfitting to the manifold in the most egregious way possible.
So you're saying the pure LLM symbolic regression is essentially cheating by just memorizing the data manifold, giving us a useless black box.
Basically, yeah. It's stringing together arbitrary mathematical operations that have zero grounding in physical chemistry purely to minimize the loss function. But MDA, because of its Bayesian Occam penalty and the void design, completely avoids this. It actually acts like a human chemist inferring the real structural equation.
Right. It recovers the exact symbolic interpretable mechanisms, like the correct Michaelis-Menten inhibition structure.
Exactly. A human chemist inherently knows that a reaction rate law has to respect physical constraints like saturation limits. MDA enforces that same parsimony. It searches for the true structural form, not just a mathematical hack.
Okay, but even chemistry in this benchmark had a pretty clean deterministic likelihood function to work with. The authors wanted to push MDA to the absolute limit. They created a brand new benchmark where the data is overwhelmingly noisy and deeply stochastic, which is biology. So let's talk about NeuronBench.
Yeah, NeuronBench is intense. It's built around generalized Hodgkin-Huxley models of neuron electrophysiology, so raw voltage traces and action potential spikes. But biological systems are inherently jittery.
Right, and that jitter destroys standard math. I mean, if your model predicts a neuron will spike at exactly 10 milliseconds, and the actual biological neuron fires at 11 milliseconds, a standard likelihood function will compare those two vectors pointwise. It'll see a massive 100 millivolt difference at that exact millisecond.
Right, the loss function outputs an astronomical error.
Exactly. It effectively tells your system that the model is total garbage, even if the fundamental biological mechanism it proposed was 100% correct. So standard likelihoods are totally useless here.
Yeah, and to bypass this intractable likelihood problem, they implement simulation-based inference, or SBI. Instead of trying to match the raw, wiggly voltage trace point by point, they simulate the data and reduce it to summary features.
Like macro-level behavior.
Exactly. They look at things like, what was the total spike count? What was the depth of the voltage sag? But for the really hard version of this benchmark neuron bench Stark handcrafting those summary features wasn't enough. They actually trained a 1D convolutional neural network to learn the summary statistics directly from prior predictive samples
Okay, wait, why is CNN?
to avoid feature collapse. That's what happens when a human-engineered summary statistic accidentally ignores the exact signal that defines a parameter. The 1D CNN acts as an amortized feature extractor. It simulates a bank of raw voltage traces, and the CNN learns to classify the structure. Then they throw away the output heads and just use the embedding as the summary statistic for the Bayesian update.
Hold on, let me push back on that. If we compress the whole complex trace down using a 1D CNN summary, what if the CNN just happens to be blind to the exact feature that distinguishes two completely novel biological mechanisms? Aren't we flying totally blind?
That is a critical vulnerability. If your CNN compresses away the very nuance that differentiates hypothesis A from hypothesis B, your system will confidently select the wrong model. And the authors knew this. That exact risk of flying blind is why they engineered a brilliantly cost-aware safeguard into the MDA system, the particle filter spot check.
Ah, okay. Let's break this down because it's arguably the most elegant part of the paper. MDA has 3 observation models it can use, right?
Right. It can use fixed handcrafted features, which are cheap. It can use the learned 1D CNN summary, which is also cheap. Or it can use a full bootstrap particle filter.
And a particle filter is an exact way of approximating the marginal likelihood by simulating latent paths over time, but it is incredibly compute intensive.
Very. It's roughly 7 times slower than the summaries. You cannot run a full particle filter on every single iteration. Your compute cost would just go exponential. So MDA defaults to the cheap summaries. It uses the CNN embeddings to rapidly iterate, but it doesn't trust them blindly. Periodically, it runs a particle filter spot check on the collected data.
It's exactly like using a cheap instant breathalyzer for routine traffic stops. It's highly efficient. But if it flags something ambiguous, you don't just guess. You take them to the station for the expensive, slow, but 100% accurate blood test.
I love the analogies today. Yeah, you need the blood test as a structural fallback. And in the benchmark, there was this scenario involving a D-type potassium channel. The cheap CNN summary heavily favored one incorrect channel structure because of how it compressed the trace.
But when MDA ran the spot check,
Exactly. The exact mathematical simulation caught the discrepancy. The cheap MAP model disagreed with the particle filter's MA kernel, so the system immediately realized the CNN was insufficient, threw it out, and fell back to the safe, slow particle filter to correct itself.
wow, so it dynamically throttles its own compute. It only spends the heavy computational budget when the data proves that the fast neural network summaries have actually failed.
Which is exactly how we need autonomous agents to operate if they are going to scale in the real world.
Right. So wrapping up this deep dive, what does this all mean for you, the researcher, or the ML engineer? MDA really gives us a path to escape the limits of passive curve fitting. By integrating classical Bayesian, rigor-like SMC and value of information with the broad, creative priors of modern LLMs, we finally have an agent that actively hunts for causal scientific laws.
Yeah, it forces us to reframe the role of the LLM. We have to stop treating LLMs as flawless oracles and treat them as highly educated guessers. MDA leverages them for creativity, but hands the heavy lifting of verification back to rigorous statistical mechanics.
Which leaves us with a pretty provocative final thought for you to mull over. If MDA can autonomously design its own experiments to maximize information gain, discover causal scientific laws from scratch, and even dynamically throttle its own compute switching between cheap neural nets and expensive particle filters, what happens when we connect this logic engine to automated, high-throughput robotic wet labs?
Oh, man.
Right. Are we looking at the first true AI scientist that doesn't just read the literature for you, but autonomously does the science 24/7 in the physical world?
It's a crazy thought.
It really is. Something to think about as the gap between digital theory and physical experimentation finally begins to close. Anyway, thanks for joining us on AI Paper Slop, and we'll catch you on the next one.